So in this part of the notes, I kind of want to follow up on some of the graph things that we started in the previous set. But before I do that, I thought I would use a graph to help you understand one of the questions that a lot of people missed on the worksheet yesterday. And it was the question about two different materials, two different isotopes, and I gave you half-lives for each of them. And then I asked you, after a year, which one would have more of the original nucleus remaining. A lot of people answered that backwards. So I thought I would use a graph to help you understand why the answer is what it is. So here's a graph where we start with 100 particles of two different isotopes, a carbon-14 and a plutonium-239. So two totally different kinds of nuclei. And one of the questions we could ask here and be able to see on the graph is, what is the half-life of each of these? Now, how long does it take to get down to half of what you start with? So since we're starting with 100 of each, we can just look and see how long it takes to get down to 50. So for the carbon-14, and I don't know what these units are, but it's less than 8. And for the plutonium-239, it's up here closer to 24. So it's got about longer than 3 times as much of a half-life. So what you notice is the one with the longer half-life sticks around longer, because half-life is how long it takes for half of the particles to decay into their daughter particles. And so plutonium has such a long half-life that it takes such a long time that the plutonium is sticking around for a while, okay? Whereas the carbon, it's going to disappear, as Tyler DeWitt would say, disappear or turn into its daughter nucleus very, very rapidly compared to the plutonium, and so less of it remains after a certain period of time, okay? So the one with the shorter half-life is the one you have less of after a certain amount of time, all right? So now what I want to do is I want to show you a different way of using some of the decay graphs. So Tyler DeWitt showed you a bar graph. I'm going to show you something else that we can do with actually a line graph related to nuclear decay. So let's take a look at that. Okay, so here's another graph that we have. This is just another nuclear decay. Now I don't have the axis labels here, but we really should. So this, of course, will be in time. And it doesn't really matter what units we use, but let's just say these are years. And what we're showing here with this graph is the amount. I don't have room over here to label this very well. So the amount of the parent nucleus, okay? So if we start with, at time 0, we're starting with about 200 units. So we should be able to find the half-life of this, right? How long it takes for us to reduce the amount of the parent by half. So if we start with 200, we need to figure out how long it takes to get down to 100. So where is that? Well, here's 100. Here's that special point. And so we have about a 10-year half-life. So remember how Tyler DeWitt noted that? T and then a little subscript of 1/2. All right? So if 10 years is a half-life, then 20 years means 2 half-lives. We should have gotten rid of half and then another half of what's remaining. So what does that leave us with? About a quarter of what we started with, right? So if we started with 200, here we lose half. We're down to 100. Now we lose half of that, and we're down to 50. And after another half-life, we go from 50 down to about 25. Okay? So we have a lot of half-lives here. And gosh, after, it looks like about 7 or 8 half-lives, if I just look way out here, you can hardly tell that you've even got anything left. This would almost be not measurable, especially after about 8 or 9. Okay? So that's a typical nuclear decay kind of a graph to be able to recognize the half-lives. Well, now let's take a look at this. It's actually the same graph. So this is still the parent nucleus. This is still going to be time in years. So you can still see we've got, that 10-year half-life. But what is this here? You see, this is something that starts at 0, and it's approaching the number 200. Well, what this is the daughter nucleus, or we've been calling it also the product after the decay. And all this is really just an upside down decay. Okay, so if you flip that over, and so what this allows us to do is very quickly find out how much of the daughter nucleus do we have after a particular amount of time. So let's use 2 half-lives as a good example. It's easy numbers to deal with. So if we start with 200, remember after 1 half-life we're down to 100, and after a second half-life we're down to 50. Well, if we started with 200 but we only have 50 left, it's like, well, where are the 150 other particles? Well, they've turned into the other nucleus. And so if we look at 20 years, what is the value here? It's 150, right? So between the blue decay graph and the orange, the growing graph, if you pick any time on there, the sum of your 2 measures will be the original 200. I'll pick, for example, let's say 30 years. This one's at 25 particles, and this one here is at 175 particles. Adds up to 200. So all it allows you to do is more quickly see an answer to a question of like, okay, how much of the daughter nucleus have we produced after a certain number of half-lives or a certain amount of time? The other thing I like about this graph, better than Tyler DeWitt's bar graph, is you can tell even in between the half-lives how much you have. So, our half-life is 10, and so we can easily see 10, 20, 30, and 40, but what about 15? If somebody said, how much will you have after 15 years? So you can just find 15 years here and go up, find that spot on the graph, and go over and read it. So it looks like we've got roughly 75 or so. Okay, so it gives you a little bit more ability to use the graph than you would if you had a bar graph. All right, so I'll give you a little bit of practice with this. You can find that practice. It's worksheet number 8 in Google Classroom. I'm going to kind of try to keep it short for you so you don't have too much to do on a Friday. Wrap that up, and then remember, if there's anything that's left that maybe from earlier in the week that you didn't get done, the lab or yesterday's worksheet or something, you can maybe wrap that up too. It'd be nice to finish the week with everything kind of buttoned up nicely. So, all right, that's going to do it for now. Thanks for watching. See ya.